So yesterday we defined the statistical learning theoretical framework. So we said, okay, we have a data set, and then we have a training data set, which consists of n data points, that point at n, and then we are assuming each of these i's are having IID from this data generating distribution with that. So the parametric like hypothesis classes, we define the risk depending on some parameter W in RD as the expectation of some loss function, where the expectation is taken over UZ. And then we define the empirical risk as the average of this loss that we observe on the training data points. Okay. These notions we defined. And I argued that maybe I should read a different.
Yes.
See if there's any other one. Yeah, I will hear that.
No, there's one red one.
So, and I argued that estimating this quantity is the most important task. And the problem is we cannot really estimate it directly because we don't have access to this distribution. And then we said we can just decompose this by using this very simple decomposition formula. And we could try to estimate the second term.
So you put inequality, yeah?
Sorry,
Upper bound.
what did I do? What?
So it's not the equality, it's inequality.
Sorry about this. It is smaller than this. And then we call this the generalization error. And the interest in estimating this is since we can numerically compute the empirical risk, and if we can get like a good upper bound for the generalization error, which can be also computed, then we can have a good understanding of the population risk, which is our primary interest in the first place. So then I introduced like the concepts in like neural networks. So what's a neural network, and then what kind of algorithm that we can use to estimate it. So I introduced stochastic gradient descent. And then, so let's come back to the second question that I wrote. And we will try to come up with a solution to the problem that we defined this. So let me just remind you the problem very quickly. So if you remember, I showed you a plot, which is coming from a true neural network experiment. So here we have the number of parameters in the neural network. As we increase the number of parameters, the training error that convergence decreased, because this is training error, or the empirical risk, they are the same thing. And then, surprisingly, the test error also decreased as we increased the, and the test error corresponds to the populations. So this gap didn't really increase as we increased the. And if you look at the authors of that paper, maybe I should track down like the reference is Neyshabur et al. 2017 called Exploring Generalization Deep Neural Networks. Deep neural networks. And what the authors also did is to evaluate existing generalization bounds, which are bounds on this generalization gap, for the exact same setup. And most of these generalization bounds behave like this. So, like this is the usual classical U-curve that we are taught in the statistics courses. So as we increase the dimension, like initially, this is the bound. And there's a nice dimension, like there's a sweet spot for dimension where it behaves nicely, and then there's the complexity of the model that dominate the error. So this is what the bound suggested. But then this is a very different picture than compared to this. So there is this observation, and then in another paper, so first I want to show you some empirical results which motivated me to take that I'm going to describe next. And there was another result, empirical result, showing this. So let me write down the name of the paper. Martin and Mahoney. Levy universality. Should I write down the whole title? Maybe yes. Levy universality. Predicts. It's very long. So then if you want to search it, then you can just type this part. But it is in 2020. So the idea of this paper was like, it's a very empirical paper coming from two statistical physicists. And then this is what they did. So if you remember, there are weight matrices in neural networks, right? So I defined like a couple of matrices. They are defined recursively. I'm not sure which one do you know. Okay.
Was good yesterday.
Maybe this is
Maybe this the red one's working, but we try to get some.
So what they did is as follows. So you take the weight matrix. So this is a neural network, right? So let's say the weight matrix corresponding to layer L. So there can be multiple layers. So they compute the eigenvalues of WL transpose W. So like you look at the singular value of this matrix. And then they observe that the singular values of these matrices, the weight matrices, have some sort of like a power law decay. Something like this. So the like the eigenvalues of this matrix. And they said, okay, let's try to fit some power law to this decay. And then let's estimate some like tail exponent alpha for each layer. And then let's combine them in some way, like taking the average in a funny way. And let's see how it behaves with respect to the generalization gap. So this was a very remarkable result. So their plots look like this. So this is the generalization error. And this is the alpha that they estimated from this power law fit. And then they show something like this, like a very clear linear trend for different networks, for different problems, for different application domains. So they tried it like on many different settings. Thank you very much. And then they showed like there's a very nice like correlation between the tail index and the generalization gap.
So this is like a log scale. What are we looking at?
So I will try to plot the exact same thing. So this is actually the test performance. So let's say we are doing classification, test accuracy. Okay. So this is like 60% to 100%. Linear scale. And then this is the estimated alpha from this power of fit. And then this is also linear scale from 1.8 to 1, something like this. So each of these points are different neural networks. So you take a neural network, you train it, you estimate alpha, and then you look at what is the alpha and what is the test accuracy that you get. And then
So you estimate alpha for the optimal weight, right? So you optimize the network, take the optimal weight, and then you estimate alpha. Is this story?
could you repeat again? Sorry.
Yeah. So the W is the optimal weight.
I mean, optimal.
Well,
you know, like the algorithm.
whatever the algorithm returns, those are
Well,
the.
I'm confused now because I thought that they have eigenvalues of this matrix.
Uh-huh.
And the eigenvalues, the biggest eigenvalues follow a power law. Or
No, like you just compute all the eigenvalues. And then you look at their distribution.
okay, so the distribution of the eigenvalues
It's like
follows
the
a power law.
eigenspectrum, and then you try to fit.
Okay, so they basically, but if you design a network, you can't just specify alpha and then go backwards, or that would be computationally hard. But it's more like this is what they observe among different examples.
Yeah, so like you just take the usual setting, you run it, and the algorithm automatically makes it like some sort of like a power law. Like
So they run many different test networks, they have many different examples, and then
Exactly.
they find this behavior. Okay.
And then like each of these points are different examples and different data sets. And then actually like they publish this in some major whatever trend, I don't know. Like I mean, people got quite excited about this.
And this is for a different Ds or the same D.
Different these.
So those points could correspond to different Ds.
Yes. So even though like you increase D, like what they claim is like this alpha is the thing which really matters, and then we should focus on this. Any questions? I saw some hands.
Different D means different size of layer also.
Yes. In different architecture, different. I mean, seemingly uncomparable things. And at this point, like when I saw this paper, I was already working on the detailed behavior and stochastic optimization. I said, I mean, this cannot be a coincidence. So like there must be a way that like, okay, so we observe some heavy tails in stochastic optimization, and there should be a way to incorporate this to the generalization bounds in a rigorous way.
And so, and are you gonna give us some intuition or your interpretation of that?
So what I'm going to do is to try to prove that like the generalization error depends on alpha in a rigorous way. So I will try to come up with a setting where we can upper bound the generalization error rigorously with some alpha appearing on the bound.
But, okay, but you're also thinking of specific model, right? So if I'm thinking in general, so you given this picture, right? So how would I explain this thing to myself? Saying if alpha is small, then, you know, some of the eigenvalues are really much bigger than the rest, and those are the important, so those are the give the important directions, etc. Sort of regardless of what D is, we have whatever 2 or 3 or 4 important directions. This is it. That's the
This is
intuition.
one explanation. So
Okay.
I mean, there are several ways which I have come up in the last, I don't know, 5-6 years. This is one of them. So if we have like a power law decay, if the eigenvalues are heavy tails, let's say they are IID from each other, like independent from each other, then by using the catastrophe principle, you can just keep the largest ones and remove the rest of them. And then this essentially boils down to some dimensionality reduction, and the effective dimension, which should appear in the bound, decreases. So in this way, we can explain it. But then today, I want to go from a different direction. Again, like it will correspond to some dimensionality reduction, but from a different perspective. But I hope that's it. Any other questions? Okay, so what I'm going to do now, I hope it will create too much anger. All right, so what I argued yesterday, if you use SGD, it can generate heavy tails, right? So I wrote this. So let's say we have this equation WK plus 1 equals WK minus step size times the gradient of some function WK. And then it also has some data points. This is K plus 1. So I'm changing notation a little bit, but like to remind you the gist. Yesterday I argued that under certain settings, under suitable assumptions, the tail behavior of W infinity will be similar to like close to T to minus alpha. And then alpha is So we chose this f to be a quadratic and then everything came from there. So I'm not going to write that to the beginning. So my claim is this. So we want to understand. Okay, so we know that heavy tails can arise from stochastic optimization. And there is some experimental evidence that like these heavy tails can correlate with the generalization gap. And we want to understand like how this can be possible. But directly working on this discrete time recursion is quite difficult. So we wanted to like simplify this a little bit, but we didn't want to lose the structure a lot. So as Anita mentioned today, one way of simplifying things is that like taking a continuous time process and then hoping that it is going to be a representative of this thing. So as a model. So from here to here, we are doing some like physicist kind of transition. And I'm going to say that I'm going to consider a stochastic differential equation dWt minus gradient fWt dt plus, let's use the one, sorry. So let's say sigma Wt d alpha t. So I'm going to assume, let's say, that the solutions of the stochastic differential equation will somehow mimic the behavior of this discrete time process in the stationarity. Because in the stationarity, I know there's going to be like having power law tails. And I want to mimic this behavior by using a stochastic differential equation because there is much more structure that I can use in this case. And to be able to have this kind of behavior, the easiest thing is to put an alpha stable process over here and then hope that it's going to work out. So, any questions about this? Like, I don't want to use a Brownian motion over here.
Yeah, it's one dimensional.
No, this is like in D dimensions, and this is the matrix valued function. And then let's assume that this is nice and everything, like the solutions are like from solution, it's like Rich-Feller and everything. Right now, like what I want to focus on is the modeling strategy rather than the technical parts. So this is the modeling assumption that we are going to do to represent this recursion in the case where heavy tails appear during the stationarity. So now this is the object that I would like to take a look at.
So, and you still hope that in the limit you get something that will minimize f, right?
If not minimize, it should be
Well,
close to some
close,
sort of
okay.
yes. But then if you try this kind of like processes in practice, you can get like similar behavior actually. Okay, so now this is a much nicer object to deal with. So now we need to define what we need to precise the exact question that we want to answer. So we want to estimate the generalization error. So our goal is the generalization error, which is this. I forgot to mention one thing. So when I was talking about the existing bounds, which is this behavior, so this is D, this is the bound. So these bounds don't take into account the data set and the algorithm choice. So they are usually just proved based on like the specific model, for instance, a neural network, but they don't care about like how the neural network is trained, which algorithm is used, what kind of data is used, stuff like this. So we want to be able to, so this is the actually like I'm guessing, I'm speculating that this is one of the main problems about these bounds, and I want to get rid of this. So by using this framework, the first question that I asked myself is how can we incorporate the effect of the algorithm choice and the data set into this generalization error estimation problem. And this is the solution that I'm going to propose now. I mean, this is already published, but proposing it for you right now. So let's say we have the process from T 0 to 1. And then just remember that we are assuming that this is a good model for through SGD in the stationarity, which means the SGD is run like for a lot of iterations and then probably near some local minimum. And you can assume that like when t equals to 0, WT is already around some local minimum. And I'm imagining like I keep running this process from T0 to T1. And I'm claiming that if I look at what's happening, like what would be the worst case generalization error? At this trajectory, I'm claiming that this would capture the effect of the algorithm choice and the dataset. So why would this capture the algorithm choice? Because WT, so I'm looking at like how the process behaves around the local minimum, and this behavior is completely indicated by the algorithm dynamics. So like trajectory already captured. And it also depends on the data because most functions that we are trying to minimize, which is also like running the process, also depends on the data. Therefore, like this trajectory has a lot of information coming from the algorithm choice and the data set. So then if we can get a good understanding of this worst case error over some, we can replace this by any finite t, doesn't matter. Then it would give us a good understanding of how the generalization error would behave given this algorithm choice and the data set. Any questions up to this point?
Yeah, the noise on this SDE does not depend on the data, right? It's just in the gradient data appears.
Yes, but it's just like a modeling strategy. So
Yeah.
I'm not saying this is a rigorous thing. Yeah, so that's
Sure.
basic for sure. So let's now give the theorem first. Okay, maybe first let's define some terms that I'm going to start proving the theorem. So who is familiar with mutual information? Mutual information. So let's say we have two random variables x, y. So let's say p x, y is their joint distribution and the px and py are their marginal distribution. We define the mutual information between x and y as the KL divergence between their joint and the product of their margins. So this is the mutual information. So if x and y are independent from each other, then this is equal to 0 because then the joint is product of margin. So it is a measure of like the dependence between two random variables. We can further extend this to alpha mutual information. And who is familiar with alpha Renyi divergences? Or so instead of KL, just imagine there like a more like a richer family of divergences for probabilities. It is indexed by some positive value alpha, and when alpha tends to 1, it corresponds to the KL divergence. And then you define the alpha information by using this Renggi divergence. And finally, we have a notion called the total mutual information between X and Y. And this is the monotonic limit of I alpha when alpha goes to infinity. So this is just a measure of dependence between two random variables. So they have different strengths, they have different meanings, but the gist is the same. So the meaning is the same. So having defined this, now I can write down the theorem. I'm going to skip some assumptions and then I will define the assumptions later on actually. So theorem. I can give like two references for this theorem. So we proved this in one paper and then simplified in a different afterwards. This is me. So under assumptions, I will come back to it later. Or sufficiently large n with probability at least 1 minus delta gamma supremo t in 0, 1 and the worst case generalization error is smaller than would be alpha of n plus I infinity I need to define this in a second. Log 1 over gamma over n, square root of n. So let me first define a couple of things and then we can discuss the meaning of this result. Okay, first of all, B, we are assuming, I also used the same thing yesterday, we are assuming the loss function is an infinite norm of loss function bounded by B, so B is the weight of bound. Alpha is the same alpha in the, also we are assuming alpha is strictly larger than 1. Alpha is the same alpha in the alpha stable process. This is the confidence term coming from here, log 1 over gamma. And this term is quite interesting. This is the mutual information. So W01 is the image of the process. So we defined it like this. So it's just a set actually. So it's W in RD such that there exists a T in 0, 1. WT is equal to W. So I'm just collecting all the points traversed by the trajectory in a set. Okay, so it's not the trajectory, it's just like I'm just collecting everything and putting it into the same set. So this is a set, and this is the mutual information term between this set and my training data set. So the bound says two things. So the last term is quite typical. So like this is just some from the confidence. It's not very interesting, but the first term is saying that there will be a term coming from the alpha stable process. And then as the process becomes heavier tailed, this term is going to be smaller. So then in terms of heavy tails, this term is going to be benefiting from the heaviness of the tails. This is quite interesting. And the second term is that if the trajectory of the process statistically depends too much on the training set, this term is going to be large. So then this might dominate. But if the trajectory doesn't depend on the specific choice of this data set, then this term might be negligible too, or like small, or like we don't really know. Like it can behave differently. And this is the gist of the bound. So any questions at this
So
point?
everything is about the SDE, right?
Yeah, this one is like completely for the stochastic differential equations. And there is a lot of assumptions. I'm going to define them. Yes.
Yeah, so there are a few things. Okay, so first of all, so the assumption, I guess maybe you say, so the S is chosen at random from some mechanism like, is this correct?
Yes.
From, let's say, for example, from the population or something,
So S is the data set which contains my data points.
right?
So and each data point is coming IID from some unknown distribution.
Okay, so this is the randomness of S.
Yes.
So the randomness of S and the randomness of W, whatever, of 0, 1, come from the randomness on S plus the randomness of the algorithm.
Stable process. Yes.
And their probability is the probability with respect
To
to
the joint.
the joint, to the choice of the data
Yes.
and okay. Thank you.
So this is with probability 1, right?
No, this is with probability larger than 1 minus.
Okay.
Any other questions?
Yeah, like I was wondering like the role of the data in the probability measure. So it's like the data, this is conditioned on the data, or this is, you assume here that the data themselves are random?
I mean, like in practice, so since we are using this SD as a model to the true recursion, so the tail index will depend on the data, right?
Yeah.
So we actually like this alpha will depend on data set too.
But you also write for large N, and N is like the size of the data set. So it's just,
Sorry?
N is the size of the data set. So you write for large N. So I was just curious if the data themselves, you keep them random in this setup, or you condition on the data.
No, we don't want to cheat on, and like this holds. I mean, like with probability 1 minus delta, this thing holds for the randomness, so they are not really conditional. But then we need a large enough N.
Sure.
So like
Yeah,
this
yeah.
probability is over mu z n-fold. N.
Yes, okay, thank you. That was the, you said like with high probability, but with what probability? But you answered it, yeah.
Yeah.
Just wondering how this result goes with the picture that you just showed us before. Because here you had big alpha there and the generalization error was becoming smaller. But here it's, yeah.
Okay, maybe I drew the picture wrong actually, the first one. So it was the test error.
Yeah.
So for smaller alpha, the test error was small. So smaller alpha is better in this picture, right? So test error,
Yeah.
large error,
Yeah.
is bad. Small error is good, and then what did I do?
Exactly.
No, but your axis was not error, was
So
the.
it
was accuracy.
Okay.
That's my fault. So this picture was suggesting like small alpha would be better for performance. To make it clear. And how does this resolve, at least resolve the problems that I described? First of all, if you think about the plot where we increase D and look at the bound. So assuming this term is going to be nice, so this is a big mystery. Maybe this will be a topic which we can discuss in the next weeks. This term is not going to depend on D, right? So the alpha is actually like what is, I mean, alpha is measuring like the generalization error in this case, assuming like this term will be manageable. And then the bound is not going to explode. I mean, it is not necessarily going to explode if we increase the number of parameters, because like this alpha is going to be like small. And then like maybe if we can control this term, then this bound is going to be nice. So this is providing some partial solution to this like dimension problem. Second, by using this kind of model, at least we can make this observation rigorous under the assumption of like under this very restrictive setting of stochastic. Okay, so this is the bound, and then we will try to prove this tomorrow. So before starting the proof, I will need to describe some notions that we are going to use this later. So now fun part is starting. So who are familiar? Yes.
How strong are the assumptions hidden in this?
So I will describe them one by one.
Okay.
Yes.
Yeah, so the division coefficient sigma in the SD, does it play a role in the bound?
We will need to put some assumptions on it. Yes. So first of all, like this SD is obviously, and then we will need to use some results of training processes. So it's nice. And then I will put a very specific assumption on the sigma, like at some point. That's right. Okay. So who are familiar with fractals? This is going to be the fun part. So let's draw a picture. Why am I using the same?
Is it one?
Is it me or?
Which lab?
Should I clean the board?
About to give up?
It's a way
Maybe
more.
the board is cleaned. Are you writing that after?
Yeah. Okay. Which one I try it's
But these.
I'm this one. Is it the way I hold it? Okay, so let's draw some pictures. So I drew an equilateral triangle, my amazing drawing skills, and I keep drawing the same thing for each of these.
Something fractal.
Sorry?
Something fractal.
Yes, it's going to be a fractal. So then if I keep doing this, it's going to be interesting object which repeats itself like many times. Want to know the name of this?
Sierpinski.
Yes. I think it's Sierpinski, right?
Sierpinski.
Yes. I or why?
It's good.
Okay, so if you measure this like a two-dimensional, if you measure this object, like the two-dimensional Lebesgue measure of this object is 0. One-dimensional Lebesgue measure of this object is infinite. So my question is, what is the dimension of this object?
4/3.
Sorry?
4/3, no?
4/3. I mean, it's not an integer, right? So this is my point. So like the objects with this kind of structure, like we call them fractals, they don't have a very like a specific definition. So Mandelbrot called it if the fractal dimension that I'm going to define is different than the ambient dimension. It's not an integer, we call it a fractal. And then, okay, so we have this kind of like fractal objects, and to define, like to measure their dimensions, and then in some senses their complexity, different notions of dimensions have been proposed over like. So one of the most used notions for dimension is box counting dimension. So we are going to use all of this here. This way I'm defining it. It's the box counting dimension. And it's defined as follows. So let's say we have a bounded set F in R3. We cover this set. So we fix a delta positive. We cover this set with some balls. Or let's see, with some balls such that their diameter is equal to delta. Okay, so when we cover the set with like open closed symmetric balls with diameter delta. And then let's call the smallest number of coverings, such coverings, as n delta. So this is the smallest number of balls with diameter delta to cover the set F. So we define the upper box dimension as the lim sub as delta goes to 0, the log n delta over log 1 over delta. So this means if I reduce the radius of these balls, what would be the increase? Like, I mean, the number of balls is going to increase exponentially, but what would be the rate of this increase in the number of balls? So then this is going to define my dimension. So if I'm in three-dimensional space, then if I just try to cover objects with smaller delta than like delta over 3, then I would need like a cubic number of balls to be able to cover the same object. So this is called the Minkowski or the upper box dimension of set F. Okay. So there is one more dimension notion that we are going to use. We are going to use this explicitly, and the things that I'm going to define now, we are not going to use it explicitly. And it is called the Hausdorff dimension. And the definition of Hausdorff dimension is slightly more complicated. So let's do it too. I'm not going to use the exact definition of this, but I'm just going to define it for the sake of like completeness. So again, let's say we have an F. Let's say it's bounded. It doesn't have to be bounded. This way. So we fix delta positive, and then we consider countable number of coverings AI such that the diameter of each of these AIs is smaller than delta. So this time I'm not setting it equal, but then this time I can take like smaller sets. And then they don't need to be bold, they can be like whatever. Such that it's the cover. So I first introduce an intermediate notion. So for S non-negative, I introduce this H S delta of F as I sum up the diameters of these sets AIs to the power S. So given an F, I covered the set F with some small sets. I put a constraint on diameters, and then finally I sum up diameters to the power X to the power S, and I look at the minimum of such value and the infimous taken over the countable covering sales. So now we define what we construct. So we take delta T here, and we define the Hausdorff measures, which is an outer measure, as the monotonic limit of this intermediate point. So this is called an Hausdorff measure. So the S is going to be important for us. So for instance, if S is an integer, then Hausdorff measure coincides up to absolute constants to the Levy measure. So this is like a strict generalization to the Levy measure, non-integer S. Okay, so this is a measure, and then this is a measure for the set F. And now by using this measure theoretical notion, we are going to define the Hausdorff dimension. So it turns out the Hausdorff measure behaves this way. So if you look at HS of F for different values of S, okay. So you start from plus infinity. It's not strictly true, but like I'm just trying to illustrate the behavior. You start from plus infinity, and at some point you directly jump to 0. And then after that point on, it's going to be 0. So the point where the jump is happening is called the Hausdorff dimension for the set. So we call this point as in H.
You can probably jump to a finite positive value, right?
Yes, so the jump can happen in 3 different ways. It can be infinite here, it can be 0 here, it can just land somewhere in between. Or it doesn't need to start from infinity actually if it's 0 dimensional. That's true. But then like this is the general picture of the Hausdorff dimension. So it's a very different way of defining the dimension, but they are obviously very related concepts. So let's define this like completely, and then
So for the Sierpinski triangle, the two are the same? Counting in the
yes, they are the same. Because it's a very nice structured self-similar object, so then there's nothing.
Log 3 over log 2.
Log 3 over log 2.
Okay. Well, that's non-integer, I guess.
Is another story.
Yeah, right.
So just to be complete, the dimension of F is defined as the largest S such that HS of F is larger than. Try to find this point. Okay, so we define 2 notions for measuring some sort of complexity of fractal sets. And then how is this related to the problem that I described? So is there anybody has some idea like where this is going?
It's probably the dimension of this trajectory set.
Yes, true. Okay, so let's make this a bit more clear. And then, I mean, I'm just going to give a couple of examples, and then I'm going to finish for today, and then we will prove it tomorrow. So why is this thing interesting for our case? So let's take an extremely simple alpha stable process, like rotationally invariant stable process in dimension D. You can see the alpha. So how does this process behave like in dimension 1? Well, actually, I will show you some pictures, but maybe I can do it tomorrow. So in 1960, I don't know how they came up with this. Volumetric negator just wrote this all over the box. So as before, let's define as 0t as the image of the process. So this is a set. We completely forget about the time axis. So we look at the points x such that LT of x, LT is equal to x for some t is 0 t. This should take it. So I'm just collecting all these points into a set and I'm looking at it. So what they prove is as follows. If you look at the Hausdorff dimension of this set, it is exactly equal to alpha almost surely.
For any D or is D fine?
For the large. What? So this is an amazing result, which essentially says that. So if you, the tail behavior of your process also affects its topological properties. So the way it covers the space is going to be determined completely by its tail behavior in a way. And the number of balls that you need to cover this process, for instance, is going to be related to its tail behavior. So like if you have the process put into tail, and then you need the balls, the number of balls cover this process depending on its tail index point. And then this was our starting point. And then this is an amazing result. And tomorrow we are going to make we are not going to use this directly, we are going to use something more sophisticated, but the idea is exactly this. So instead of having square root of x in the generalization bound, so like in the usual bounds I said we have this thing. Our goal would be to replace this t with this new dimension. Yes.
But isn't this result mostly due to the small jumps of the alpha stable process? So you could truncate the jumps and this would still hold.
But then, like for this specific case, like it's homogeneous, so it's fine. But it's a good point. So actually,
So I mean,
okay,
my question
let's
is like,
discuss
this, okay.
it's because of the small jumps, but again, like it's the how the jumps behave. Like again, like there's like power with the.
Yeah, it's zero.
That's true. That's true.
So you can replace your process, your driving Levy process with something that looks like alpha stable near zero, that has, let's say, bounded jumps, or no jumps at all, or clipped jumps, right? Like this clipped SGD. And would the conclusion still follow? Like some of it.
Maybe we can talk about this later. But like for the case I chose, everything is like more sterile, so then it is easier to deal with. But this is important.
Because for Brown motion, what would be the dimension again?
2. So yeah.
Essentially, the phenomenon that you're trying to explain would have replaced.
Yeah, I want to replace this t with something reasonable and related to the pain index, and then what we have.
So your SDE, you could have just taken Brown motion.
Sorry.
Your SDE
Uh-huh.
would work if you just take Brown motion and then you would stay. You would still remove the D.
That's true, but
Right.
More like in dimension two.
It's still you.
I mean, it's also like
Recurrent versus transient.
improving over like other generalization bounds for the case where alpha is 2. But then my main goal was to like have some like tail behavior in the generalization bound. That's why I didn't really focus on the case alpha. Okay, so any questions before we finish? Then we will move it to one. By the way, this is not the only one that I'm going to do. So like this was the first thing that we did, and then more thing. So let's get. Yeah.